Okay, welcome back. We're going to continue our discussion of motion in one-dimensional kinematics. I dropped off my parenthesis there. And in the previous video in this sequence, we looked at position and time, and said that those were fundamental quantities that we needed to have in order to describe motion and measure it. They both needed to have some kind of coordinate system with a fixed origin. So we have to have a zero value for time, like the start of a race, noon, or rather midnight on January 1st, 2020, or the instant that fusion began in the sun, the instant of the Big Bang, the instant the bell goes off at the beginning of class, whatever. And we need to have an origin and frame of reference for position, a place that is considered zero, that everything is measured relative to for position. How many meters, how many feet away from that point, and in what direction. And we looked at how position changes with time, and we defined a quantity called velocity, which is the rate of change of position with respect to time. And we saw that if we have a constant velocity, or if we're finding the average of a velocity that varies, that the way we do that is just look at the difference between the starting and ending positions and divide that by the difference between the starting and ending times. Change in position divided by change in time. That went along with the slope of a position versus time graph if you had straight lines. But that slope goes along with the rate of change as well, even when the rates are changing, even when the lines are curved, even when the velocity is changing. And so our instantaneous velocity is also the slope of a position versus time curve. But since you can't directly measure change in position over change in time, we have symbols indicating, oh, it's an infinitesimally tiny change of position in time, to represent that that's the slope at a zero-dimensional point on the graph. So we talked about position requiring a direction, and I'm using this term velocity here, and you might also be thinking of speed. And so it's important at this point that we start to talk about a couple of different classes of quantities that we work with in the physical sciences and anything where you're measuring quantities, really, called vectors and scalars. So quick definitions here. A scalar let's see, has size, or we say magnitude, and a vector has size and direction. So thus far, we've had position, the direction mattered. We can say it's so many feet, but so many feet in the positive direction, let's say to the right, or up, or northeast, or 20 degrees above the horizontal. Direction matters for position. So that's an example. That means the difference between position matters as well. So displacement when we talk about how far you've moved, like around the track or on the odometer of a car, and you're not quantifying all of the directions, because displacement, if you drive your car back and forth to work or school every day, you have 0 displacement, but if you're like me, you might log 90 miles on the car in the day, or more. So the distance you travel is some amount, even though the displacement is like 0. So distance would be a scalar quantity. Velocity is a vector quantity. We care whether you're going 30 miles per hour north versus 30 miles per hour south. Makes a difference. But if you just wanted to say, oh, you were going 30 miles per hour, that's speed. So velocity is speed with direction. Velocity is a vector, speed is a scalar. We say scalar because when you multiply them by something, it doesn't change the direction of the thing, it only changes the scale. So there are quantities that we have used here also. Time is essentially a scalar. We could talk about forward and backward in time, positive and negative values for it. But there's not like a angle off of time that's also in time. If you get into working with special relativity and you treat time, or something funky like time times the speed of light times the square root of -1, as its own 4th dimension, like the 3 space dimensions, then okay, then it's part of a vector quantity of space-time. But for our purposes, time's a scalar. Other quantities we're going to run into that are scalars include things like mass, volume, energy, power, density, temperature, all those things. There are others you can probably think of. That temperature is kind of sloppily written there. One we're going to hit that's a vector in just a moment is acceleration. We'll also see that force, momentum are examples of vector quantities. There's other classes of quantities as well besides scalars and vectors that have multiple sizes and multiple directions that you need to use matrices and linear algebra to represent, which is far beyond the scope of what we're talking about here. We call those things tensors. But we're not playing with those right now. So, the reason why I have all these arrows on the top of these quantities is to show that we care about the direction and that they're vectors. So I'm talking about velocity here. If I erase the arrow, then I might be meaning speed. If I erase that arrow, I might be meaning speed. But that's just the convention that I'm using on the board here. And you may find that other folks don't differentiate as clearly. Some textbooks put vectors in boldface and scalars in italics or something like that. It varies, the convention varies a bit. Okay. Let's take a look back at motion itself and give us some more space to work with. I said I wanted to look at what happens when we change velocity. Actually, I'm going to make that a separate video, so let's do that.